Hello, BC Calculus students. This is Mr. Johnson, and we're going to start section 8.2, which is on series. Now, in section 8.1, we talked about a sequence, which is essentially just a list of numbers. So a sub 1 plus, or a sub 1, a sub 2, a sub 3, a sub 4, and so on, just listed out. With a series, we're going to look at the sequence, but we're going to be adding up each of those terms. So we're going to have a sub 1 plus a sub 2 plus a sub 3 plus a sub 4 and so on. So it's this infinite addition basically, which is going to be a series. Now when we look back on how numbers are originally written, or especially irrational numbers such as pi, with pi we have obviously 3.14159 and so on. So it's this irrational number. And the convention behind the decimal notation that we use, especially with this irrational setup, is that any number can be written as an infinite sum. And so we could look at pi instead of the decimal form that we're used to. We could look at it as the sum of particular values. So for instance, we have 3 plus, instead of 0.1, we could write it as 1/10. Instead of 0.04, we could write it as 4 over 100, which we could write as 10 squared. And then instead of 0.001, we could write that as 1 over 1,000, which is 10 cubed. And we could continue with each of the digits for pi. Now, where I've stopped here, let me just back up and erase that 4. Looks like 104. If I was to stop here, this is close to pi, but clearly we're missing a lot of values because pi is irrational and just goes on forever and ever and ever, and I only have just a handful of decimal places that are represented here. So the idea behind this is that we're going to look at this infinite sum, this infinite setup to see every decimal for pi as far as we could possibly go. And this idea is really a series, and that's what we're going to talk about in this particular section. Now, in general, if we're trying to add the terms of an infinite sequence, remember again, our sequence has this list of terms. Well, if we were to instead look at the sum of those terms listed out, we may want to write this in a slightly different notation. For instance, we're going to use sigma a lot, where we have, for example, n starting at 1. N doesn't need to start at 1. It can start at 0 or 2 or 7 or whatever. But we have this generator a sub n, and so we're signifying that our first term is going to come from substituting in n as 1 to our generator, which gives us a sub 1. That's going to be n equal to 1, our first term. Then we're going to add, and then we have n as 2. N is our counter. N is going to be counting through the whole process. N is 2, that means we have a sub 2. That's, again, our second term. And then we have a sub 3, and you get the idea. We're just generating all of these terms infinitely, and that is considered our series or our sum. And so we're looking at whether or not this type of series is going to converge or diverge. So in other words, do we get an actual sum that we can understand, or do we not get a sum? Is it never going to add up to some value? Now, occasionally, we're going to be able to figure out this infinite set of numbers added up. We're going to be able to figure out exactly what it sums up to, which is a very unbelievable thing to be able to do, is to take an infinite addition and actually assess what it actually adds up to. Other times we're going to be able to determine whether or not it converges to a value, but we may not be able to find that actual value. We may not know what it actually sums up to. We may simply just know that it does converge to a sum, to a value. And then we may have stuff that's very obvious that it will never add up to a value. It will just either continue to grow or maybe continue to alternate back and forth between positive and negative numbers. And that's really our task here with series. So again, in section 8.1, we did sequences. Sequences are relatively small in the context of chapter 8. With series, we essentially build the rest of chapter 8 on this topic. So this particular section is very important as we continue our study in chapter 8. We're going to spend the majority of our time now on this idea. So let's consider this particular series. We have 1 plus 2 plus 3 plus 4 and so on and so forth. We have all these values. Does it make sense to try to find the sum? Well, the simple answer is no. because if we think about what's happening here, we're continuing to increase very rapidly, actually. As we add up these values, all of these integers, we're going to continue to increase and increase and increase. And so there will not be a sum because we'll continue to increase to infinity. What if we were to take a look at a different series? For example, we have 1/2 plus 1/4 plus 1/8 plus 1/16 and so on. I'm going to give you a geometric representation of this one. This is one that you may have seen before, I suppose, but let's say we take this square, which has sides of length 1, and I take and I divide this directly in half. So therefore, this side right here is 1/2. And then I take the other half of this and I divide that in half. So obviously this is going to be 1/4. And I have so far written the first two terms, a sub 1 and I have a sub 2 here. And then I take the next one and I divide that by half. So I have 1/8. And let's just go ahead and say that's a sub 3. And so again, I'm up here in my series a sub 1, a sub 2, a sub 3. All right, I'll do it one more time. So we have another half and we have 1/16, and we'll call that a sub 4. And what you can see is that this continuation will be a geometric representation of the series. And this geometric representation very clearly has a total, has a sum of 1, because the area of this square is 1. It's a 1 by 1 square. And as I continue to break up the interior of this square into halves to represent the series that we have listed out here, so the 1/2, the 1/4, 1/8, 1/16, and so on, as we sum up all of those values, we geometrically get a square of area 1. So this is convergent. And not only that, but the sum is 1. It has to be geometrically, just intuitively. This particular one is called a geometric series, which kind of makes some sense because I showed it geometrically, and we'll talk about that shortly. But this idea, the two ideas behind these two concepts here, one is very clearly divergent up at the top, where we're just continuing to add and add and add and add more and more and more and get larger and larger values. And here we're continuing to add, but the values are getting small enough that there will be a sum, even though we are continuing to add infinitely and forever values. Those values get small enough in the end that we do converge to an actual sum for that particular series. Okay, let's move on to the next page. All right, in this next page, we're going to begin by talking about partial sums. And I will warn you that in the first handful of concepts that I'm going to walk you through in this particular section, 8.2, there is some relatively straightforward ideas, and there is also some relatively abstract ideas. This is one that is pretty abstract. I find that students often struggle to grasp this concept fully. Often students will say, okay, well, I think I understand that. And then they come across a problem and it's really clear that the concept is not quite there yet. So it takes a lot of practice. And you will hear me say this many times, is that the only way to really understand these ideas is to practice, to listen, to learn, and then practice. So we're going to talk about partial sums. Now, the idea of partial sums is that we have a series that's listed up here, a sub 1, a sub 2, a sub 3, and we're just adding each of those terms up. The partial sum s sub 1 is simply the sum of the first term, which of course is just a sub 1. S sub 2, that's the partial sum of the 2, so the first two terms. So S sub 2 is simply a sub 1 plus a sub 2. So it's not the entire sum, it's a partial sum. Then we have a sub 3, which you can see now, and this is pretty straightforward so far, is the sum of the first three terms. S sub 4 would be the sum of the first four terms, and so on. The pattern continues. S sub n would be the sum of the first n terms. So we continue out to a sub n, but then we stop. Okay, notice up in the original series we have a sub n, and then we're continuing to add because that's just what a series is. Well, the nth partial sum is going to end at the nth term, whatever that may be. Okay, that's the idea of a partial sum. Now, we're going to list out the partial sums as a sequence. So again, the partial sums, so this sum, I don't know what that is. Whatever that value is, it's a number. This second partial sum is going to be the addition of the first two terms. That's going to be a number. The third partial sum is the addition of these three terms. It's going to be a number. So in other words, all of these partial sums are simply just numeric values, and we're going to list those as a sequence. So again, this is all of a sudden a very abstract idea. We have a sequence of sums, and we're going to continue the idea of that particular one as we go out to infinity. So we are simply writing the partial sums as a sequence, so as a list of numbers, okay? But remember, embedded, let's say, in this particular partial sum of 4 is a sub 1 plus a sub 2 plus a sub 3 plus a sub 4, okay? So that is representative of s sub 4, which is just a single term within the sequence of partial sums. Now, if we were to take a look at, let's say, the nth partial sum, so let's just assume that we're way out from the first term. We have maybe n goes out to 1,000,000 or something. The nth partial sum, if we take the limit of that is n goes to infinity. So we're taking that nth partial sum and we're making it really big. If we get a value right here, s, we're going to say that that value is the sum of the series. In other words, we're going to say that this s is equal to the sum as n goes to 1 to infinity of a sub n. Okay, again, this is a very abstract idea. Now remember, this nth partial sum is written right here. So the nth partial sum is a sub 1 plus a sub 2 plus a sub 3 plus a sub 4 for a very, very long time, all the way up to a sub n. In other words, it's very, very, very similar to the actual series itself. If n goes to infinity, it is the actual series. So if we're able to take the limit as n goes to infinity of the nth partial sum, and we get a value, a sum, a numeric value, then that sum will be representative of this series. Okay, and you can look at the summary below. I'm going to give you an example of this, and I'm going to give you a few of them here, not back to back right now, but we will have them as we practice. Here's one example, okay? And this is, again, a very abstract idea, okay? So it says the infinite series as k goes from 1 to infinity of a sub k has nth partial sums given by this formula where n is greater than or equal to 1. What is the sum then of the series? Okay, so let's just, we don't know very much about the information. A sub k is just a generic placeholder. We don't actually know what the series generator is. But if we were to look at, let's say, the nth partial sum, let's look at the first partial sum. We know that that's a sub 1. We know that the second one is a sub 1 plus a sub 2. We know the third one is a sub 1 plus a sub 2 plus a sub 3. Okay, and obviously we could just keep on going with this pattern. Now let's take a look at our generator. So we're being told not what a sub 1 is, or a sub 2, or a sub 3. We don't know what any of those are, actually. All we know is we know the partial sum generator formula. So s sub 1 in our generator formula would be negative 1 to the power of 1 plus 1, which is, of course, negative 1 to the second, which is 1. S sub 2, so the second partial sum, we would then use our formula, and we would get negative 1 to the 2 plus 1, which is negative 1 to the third, which is negative 1. Then we have the next one, which is negative 1 to the 3 plus 1, which is negative 1 to the 4, which is fourth, which is 1. We could do the fourth one. I'm not going to continue here too much, but I want you to see the pattern. This one is going to be negative 1 to the 4 plus 1, which is negative 1. Okay, what's happening? As we look at each one of these partial sum values, if we were to project this out to s sub n, we get this formula, right? What does it mean? What it means is that we're getting this pattern of 1, -1, 1, -1, 1, -1, 1, -1. So if we were to take, for instance, the limit as n goes to infinity, this is the definition just above that we were talking about, of s sub n, do we get a value s? And the answer is we do not. We get this alternating 1, -1, 1, -1 pattern, which means that the series, remember we're talking all about the series of, uh, of a sub k, that is not going to converge to any particular value, because if it converged to a value, it would have to be equal to a sum based on the partial sums, which it does not, because the partial sums go from 1 to -1, 1 to -1, and so on and so forth. So this particular series is divergent. Let's say, hypothetically, that these yellow circles that I have here are beginning to converge, and all of a sudden we get, I don't know, let's just say we get 1/2 for this value. Well, then the series would converge to 1/2. We do not get that behavior. We don't get any pattern of convergence. We get a pattern of divergence, and that's why the sum of the series would be considered divergent. Okay, let's move on to the next page. All right, we're going to talk about, and again, we're changing gears here a little bit. We're going to talk about a geometric series. This is one of the most important series that you will see in our chapter, and it's a relatively common one, and I will let you know that it's actually a really easy one to deal with. I'm just going to show you the generic form of it. So it's a plus ar plus ar squared plus ar to the third, and so on. And we get ar to the n minus 1. It could be ar to the n, by the way, but I'm just going to write it that way for the sake of a little proof that I'll show you in a minute. And so our generator here is ar to the n minus 1, and we're going from 1 to infinity. Now we're assuming that a is not 0, so a is some value other than 0, and we're looking at this basic form of a geometric series. Now the common ratio is the item that we are multiplying every single term by, and that ratio, as you can see algebraically, is going to be simply r. So in other words, if you take the very first term, a, you multiply by r to get the next one, you multiply by r to get the next one, you multiply by r to get to the next one, and so on. So the common ratio is r. And if we were, actually, I'll back up, I'll talk about the restrictions in a minute. If we were to look at the nth partial sum, so we're going to say, we're just going to make one restriction so far, and that is that r is not equal to 1. Okay, so if we have s sub n, we have a plus ar plus ar squared, and so on. We could continue, obviously. And then we're going to get, let's just make it ar to the n minus 1. So that's going to be the nth partial sum. So we talked about partial sums just a second ago, nth partial sum. Okay, let's say we multiply that entire equation by r. So we end up getting r times n sub, or s sub n. And then I'm just going to move this slightly just so that you see the behavior, what's happening. So again, I'm taking the entire blue equation, multiplying every term by r. So I get ar plus ar squared, and so on. This this term that we had right here is going to be actually ar to the n. So let me just make sure everyone understands. So I'm taking s sub n multiplying by r, so I get s sub n times r. I'm taking a times r to get ar. I'm taking ar to get ar squared. I'm not writing this one down because that would be ar cubed, but I'm not going to bother with that. That's just in the middle here. I get this term I didn't do anything with, but if I take this term and I multiply by r, now it's going to be r to the n minus 1 times r, which gives us ar to the n. Okay, so essentially what we're doing is we're shifting this one over just slightly. Okay, but again, all I'm doing is multiplying the entire equation, every single term by r. Keep in mind there's this huge void that we're not representing just because it is this enormous series. Okay, if we were to take them and simply just subtract the green one from the blue one, so I'm taking and subtracting them. I get S sub n minus R S sub n. Can't do too much with that right now, so we'll just leave it like that. Then I get A, so A minus. Now when we take AR and subtract AR, we cancel, which is the reason I wrote it this particular way. AR squared minus AR squared cancel. All of these little terms in here are going to cancel. This term minus AR to the n minus 1, those are going to cancel. And really, I'm going to be left with this term here, which is AR to the n. So there are many, 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 many terms that end up canceling. In black, that's what we have left over. Okay. Now I'm going to factor out the S sub n. And we're going to go ahead and, whoops, we're going to divide by 1 minus r so that we get S sub n equal to a minus AR to the n over 1 minus r. Okay, so we just talked about how, when we're looking at this particular geometric set, we know that we're focused here on n going to infinity. So what I'm going to do is, let's move up here for a second. I'm going to let n go to infinity, and we're going to take a look at this particular limit, a minus AR to the n over 1 minus r. If n goes to infinity, we know, based on what we were studying in section 8.1, and I'll just write it over here on the side. So from section 8.1, we know that if r is a value that is between, let me change this, hold on, between -1 and 1, including 1 but not -1, we know that that particular sequence is going to converge. Okay, now we know that the sequence will converge to 0, and this goes back to section 8.1. So if the sequence converges to 0, then r is between -1 and 1, but not including either one, and the sequence is convergent to 1 if r is equal to 1. Okay, now what we're going to do here with a series is we're going to eliminate the value of 1, because if you think about r equal to 1, you're going to have a divergent series, and I'll talk about a little bit more about that in a second. So we're going to look specifically at these values here between -1 and 1. So if r is between -1 and 1 but not including either one, then as r to the n is going to go to 0 as n goes to infinity. Okay, so as n gets really large, r to the power of n is going to go to 0 if r is between -1 and 1. So what that means for our limit is that this value right here is going to go to 0. And what we will get is a divided by 1 minus r. And again, we are putting a parameter here of r between -1 and 1. Another way to say that is that the absolute value of r is less than 1. Maybe a little bit faster way of saying that. Okay, so what we have is, again, based on this equation right here, we have S sub n equal to a over 1 minus r. And remember, we had the idea from the previous page that we take the limit as n goes to infinity of S sub n, and it is equal to a value s, then the series is going to be equal to that value s. And we just showed that that value s, that sum, is equal to a over 1 minus r. And this is a sum that you're going to want to memorize. This may be familiar from honors pre-calculus. I have no idea if you remember it at all, but this is talked about previously but often forgotten. This is the sum of a geometric series. Now below you have the formal definition of this, and it does show the restriction. I'll highlight it here. So the restriction is that r is less than 1, then it's going to converge to a sum of a over 1 minus r. Now, if R is not in that range, okay, then it's going to be divergent, which is really, really important because guess what? You could take a divergent geometric series and you could utilize the sum formula and you'll actually get a sum out of it, and that's an incorrect sum. So you have to be very careful to check the restriction first and then calculate the sum, and I'll show you examples of that in a minute. We call this the second convergence test. Now, you're going to have 10 convergence tests across our sections that we're going to study, not just this section. You're going to have 10 convergence tests. This one is the first one. Excuse me, the second one. The first one I'll talk about in the next video. But this is the second convergence test, the geometric series convergence test. Okay, let's do an example. After all of that proof and conversation, let's do an example. So we want to find the sum of the geometric series. The first step is to find the common ratio, which is R. And some of you can look at this and you can determine what you multiply 5 by to get negative 10 thirds, and then what you multiply by to get positive 20 over 9, and what you multiply to get, and so on. Others can't. And so what we're going to do is we're going to just make sure you understand that a common ratio is calculated by taking one term divided by the previous term, and it has to be consistent throughout. So obviously you can't pick 5 because it doesn't have a previous term, but if you pick, for instance, negative 10 thirds and you divide by the previous term, which is 5, you get negative 10 over 15, and that gives you negative 2 over 3. And you can double check that if you were to take negative 2 thirds times negative 10 thirds, you do get 20 over 9. And then you could take times negative 2 thirds again, and you get negative 40 over 27. So that's an algebraic way of finding the common ratio. Most often you can do it by observation. A is the starting term, which is 5. Now the first thing we want to double check, does this fit our restriction? And yes, the absolute value of R is less than 1. So we're happy this is going to be convergent. The sum is going to be A divided by 1 minus R, which is going to be 5 divided by 1 minus a negative, so plus 2 thirds. A really fast way to calculate this is to multiply both top and bottom by 3 just to clear your fractions. So you get 15 over 3 plus 2, which is going to be 15 over 5, which means that the sum of this particular series, as unbelievable as it is, if you were to take and add this up infinitely forever and ever, you would end up getting 3. So it's convergent to 3. All right, let's try the next example. So it says, consider the particular series. Is the series convergent or divergent? And if it's convergent, what does it converge to? Now you can see that that based on our generic geometric series, this doesn't quite take on the form of the sum of a r to the n minus 1. And so we do need to do a lot of tweaking with this one. We have to figure out what it's going to look like. So the first thing that we can do is, instead of taking 2 to the power of 2n, we can make that, and this just takes practice, by the way, and just looking at lots of examples, we can make that 4 to the n. And instead of 3 to the power of 1 minus n, we can make that 3 to the first times 3 to the negative n. Okay, that may not seem like it's very helpful yet. The next thing that we could do is we could take and make it 4 to the n divided by 3 to the n times 3. And I'll move that 3 to the front because it could actually be moved all the way to the front, but we'll leave it like that. And we can make this 4 thirds to the power of n. So what we're doing is we're trying to transition ourselves into this idea of a times r to the n, or a times r to the n minus 1. And you can see now that we're in a better form to analyze the problem. More specifically, you can see that if n, based on the problem, and as how it's written, n is equal to 1, and we're going to infinity. And so we know, essentially by looking at our new form, that r is 4 thirds. So then the question is that in a convergent restriction or divergent? And because this is greater than 1, this particular, and it still is a geometric series, is divergent. And so we don't want to worry about finding any kind of sum because a sum does not exist. Now, just to make sure you understand, if we were to take a look at the formula for a sum, And we said, well, okay, I'm going to let a be n equal to 1. So that means a is 4. So if n is equal to 1, put in 1, you get 3 times 4/3, which is 4. My r value is 1 over, so it's, or 1 minus, so it's 4/3. And guess what? We actually get a number out of this. So if we multiply by 3, we get 12 over 3 minus 4. So we get negative 12. And occasionally we take that and we say, well, that makes a ton of sense. We're going to get a sum of negative 12. Well, if you think about it, every single term here is positive. That doesn't even make sense that you would somehow get a negative. But number two, it's divergent because the R value doesn't fit the restrictions that we have in place. So it's really important that you don't just jump into a calculation of the sum. You must test whether it's convergent or divergent first. Then you can test the convergent value. Okay, let's move on to the next page. All right, example 4, what is the value of that particular series? Now this one's much more obvious that it's geometric. Often when it says what is the value, it's geometric. More often than not, it's going to be geometric. There is another alternative that I'll show you in a different video where you can find the sum and it's not geometric, but if it says what is the value or what is the sum, it's almost always geometric. All right, the R value is pretty obvious. It's negative 2/3. Remember, the a value is the starting term. So if n is 0, and pay attention, we haven't had a lot of n is 0s yet. So n is 0, we get an a value of 1. Now the first step, let's make sure we know if it's convergent or not, because letter E on this problem is that it's divergent. So the absolute value of r is less than 1, so we're happy it's going to converge. Okay, and we have our sum. Our sum is going to be a, which is 1 divided by 1 minus negative 2/3, so 1 plus 2/3. We could do our algebraic technique of clearing the fractions, so we get 3 divided by 3 plus 2, which is 3 over 5, and that's option C. All right, let's take a look at example 5. This is a little bit more abstract now, so we did a couple of those geometric series problems, which are a little bit easier to do. This is a little bit more abstract. This is a repeating decimal. You've seen this before in mathematics, obviously, where you have just the 1 7 1 7 1 7 1 7 repeated. We're going to look at it as a geometric series. It doesn't appear to be that necessarily right now, and we're not going to be concerned at all about the 2.3. That's not part of our geometric repetition. We're going to take a look at that 1 7 1 7 1 7 1 7. The first 1 7, this is kind of connected to what we did with pi at the very beginning of the video. So the first 1 7 is actually in the thousandths place, which is 10 to the third. The next 1 7 is going to be in the 10,000ths place, and which is going to be 10 to the fifth. And we have this pattern continue, as you can see in the problem. All right, if you take a look at this little portion right here, let's just forget the 17 for a moment, okay? We're just looking at the 1 over 10 cubed and 1 over 10 to the fifth and 1 over 10 to the seventh and so on. We can see that the a value is clearly 1 over 10 cubed and the r value is 1 over 10 squared, which obviously 1 over 10 squared is within our range of a convergent series. And so if we were to look at just that portion and the sum of that portion, we would have 1 over 10 cubed divided by 1 minus 1 over 10 squared. And if we were to just algebraically simplify this and multiply by 10 squared, we would have, oh, actually, you know what? Hold on. Let's multiply by 10 cubed so we can actually clear the whole thing rather than 10 squared. So we have 1 in the numerator, and then we have 10 cubed minus 10 cubed over 2 is going to be just 10. So I'm just simplifying by multiplying this through like that. Okay, 1,000 minus 10 is going to be 990. So we have 1 over 990, and that's representative of that phrase that we have, the repetition, the geometric series portion of this number. So what I'm going to do is I'm going to put all this together now. So we have 2.3 plus 17 times what we just got. So we have 17 over 990. And what we've done is taken this repeating decimal with a geometric series approach, written this as a small decimal, but then plus this fraction. If we were to combine these, and I just did this with a calculator because the numbers were so large, but you get 1,147 divided by 495. This is actually an error, by the way, in your answers in this section in the back of the section, but this is the fraction representative of the 2.317 repeated, and this is done by using geometric series. Right, in example 6, we're going to do one using the geometric approach, and this is actually one that you want to star and come back to because this is a power series. This is going to be a huge idea in the second portion of this particular chapter. So we're talking about it now in this section because it's actually a geometric problem, geometric series problem, but we're going to be using this problem. This is going to be one that you're going to memorize. This is going to be one of the most important series that we're going to utilize in section 8.5 and after. So in this particular case, let's just list it out. So if we were to list out terms, n is 0, so we get 1 plus n is 1, we get x to the first, plus n is 2, we get x squared, plus n is 3, we get x to the third, and so on. We get x to the n, and then we just continue on, okay? If you can use these geometric series ideas that we just developed, you can see that a is 1, and r is the value we multiply by every time, which is clearly x. And if we were to set a restriction of the absolute value of x is less than 1, in other words, it fits into the proper restrictions of a convergent geometric series, then what we get is a sum of 1 over 1 minus x. And this is a huge idea when it comes to power series, because what we've essentially determined here is that the rational function 1 over 1 minus x is equal to an infinite series, an infinite sum, an infinite polynomial that is representative of this particular series. And that's an amazing idea because we've studied polynomials for years in mathematics, and here we have a rational function that is equal to an infinite polynomial, which is a very amazing idea. And so we study that in the second half of chapter 8, but you can star this because we're going to come back to this one. Okay, that's the first portion of section 8.2. Thank you.